Welcome to this mini lecture here on work and power. I'm going to introduce you to a couple of basic ideas um, about the energy without really talking about energy too much or defining it. So these are kind of some preliminary things. And it's a little bit tricky because we use these words in everyday life, and as frequently is the case whenever you have an overlap between everyday life language and the way scientists use it, you have to tighten it up, right? So the biggest one is that work is really not in physics language about effort or about how much energy you yourself are using up, or how hard it is for you. If you think about it, that's a little bit too subjective a definition for science. And so we're really going to tighten up. The work is actually involves you actually having an impact on what you're pushing around, right? So like, for instance, if you push against a wall and the wall doesn't move, you might get tired, but you're not going to do any work because you weren't effective in moving the wall, right? So you need two things in order to accomplish actual work in physics. And that is you have to apply a force so that your effort is involved, and you have to displace the object in some way, right? So we're basically going to have to multiply these two things, force and displacement. Of course, these are vectors, so it's time for us to actually look at the math a little bit of how to multiply vectors, all right? And now one of the reasons why we've been avoiding it thus far is, well, first of all, we haven't needed it yet. But the other thing is that it's a little bit more complicated than adding or subtracting vectors, in that the term multiplication is basically overly broad, right? And there's a couple of different ways that you can think about vectors interacting when you want to multiply them. And formally, they're known as the dot product, right? Which is just gets its name from the fact that you're going to represent multiplication with a dot. And the cross product, which is usually the first way people will see multiplication, which is with this cross, right? And of course, in scalar math, these symbols are interchangeable, right? They just both mean multiplication. In vector language, you have to have one symbol or the other. You can't just list the two variables side by side like you can do for scalars implying multiplication, because, as you'll see, these are very different types of multiplication. So the dot product basically is saying, I want to multiply these vectors to find out how much these two vectors are working together. And in the cross product, you want to multiply these two vectors to see how much they can rotate each other. So in a broader sense, A dot B is asking about the parallel components of those two vectors, and A cross B is asking about the perpendicular parts of those vectors. All right. Now, it turns out we only need one of these for now, which is the dot product. So let me explain why we would want the dot product. So our job here is to think about the fact that I'm displacing an object, I'm doing work to it because I'm applying a force and I'm displacing it. And then the question is, do I want the component of the force that is perpendicular to the displacement? That would be like going up in this picture. It's not the component that is not pictured here, right? Or do I want the component that is parallel? And if you think about it, the part of the force that's perpendicular is just going into sort of lifting the weight, partially lifting the weight of the crate off the floor and reducing the normal force. It's not actually responsible for any of the displacement. It's only the x component, or the component parallel to the ground, or more generally speaking, the component parallel to the displacement, that's actually responsible for moving it, right? So we want to pick out the parallel component. And so that's why we want to use a dot product. So we're not really introducing any more math here because you already know how to find the components of these forces. We're just sort of like being a little bit cleaner about what it means to multiply them, right? So when we say we wanted to take the dot product between any two vectors, in this case specifically force and displacement, which is how we're defining the work done, that we want to find the components of the force that are parallel to the displacement. Or, of course, you could say the component of the displacement that's parallel to the force. That will give you the same answer. Notice that this dot product is now going to remove the directional information, right? Because now what you're doing is you're multiplying two things that are in the same direction, and so there's no directional information in the result. And so work is actually a scalar. So this dot product is kind of an exception to the rule that I had told you earlier, where if you have an equation with vectors on one side, you have to have vectors on the other side, because if you have direction on one side, you need to have direction on the other. And the way I can get by with saying that without lying to you is because this dot product actually gets rid of the direction, right? So even though you do have vectors on the right-hand side of this equation, there's no direction associated with the overall dot product any longer. All right, so here's a question. Maybe you want to pause it now and before I talk about the answer and see what you come up with. Okay, so this is a question about units. So we just need to think about the formula that I just showed you, F dot D, and if we're going to measure work in joules, that's the metric unit for work, what would it be equal to? And the first answer that I would think of is Newton meters, letter B, and that is a correct answer, right? Because you get the units of newtons come with the force, and the units of meters come with the displacement. Unfortunately, when you list units like this, because the units themselves are scalars, they don't use dot or cross products. And I say unfortunately because I feel like sometimes it does matter, but formally speaking, you would not have a dot or a cross product here because we're just describing units. So this is newtons dot meters. If you actually do a cross product between force and displacement, you get the same units, right? But there actually is very different physical meaning, so that's why I said unfortunately. Now, the reason why this is not the only correct answer is because Newton is not a fundamental unit. Remember, the fundamental units are MKS, meters, kilograms, seconds, and eventually we'll add C for coulombs for charge when we start talking about charge. And then those 4 units basically cover just about everything. Well, they cover everything we'll talk about in physics. In all of science, the SI metric units, there are 7 base units, right? So you got meters, kilograms, seconds, coulombs, and then a few others, like the mole and stuff like that to round it out. So if you reduce this, Newton is a kilogram meter per second, so you're going to pick up that second meter, and so you get D, so the best answer is letter E. All right, so formally, this is mathematically how you take the dot product. You have 2 ways of figuring out which components are parallel to each other. This super formal component method we honestly probably won't need to use, but this is the most sort of formal. If you have the 2 vectors already described in component notation, this can be convenient. And of course, this is also convenient if you're writing computer code or you want to do it with matrices or something like that. And that is just take the x components of each, multiply them out together. If one of them doesn't have an x component, you'd have a 0 there, and that term gets eliminated, right? And so just by multiplying the 2 components together and adding them up, you are effectively pulling out just the parallel components because the zeros will take care of the directions that aren't in both vectors, right? The more straightforward way, and this is usually what we wind up doing, because usually when we're given vectors, they're described in terms of magnitude and angle, right? And so if you picture this gets back to this is very similar to the picture I showed you of the woman pulling the crate across the floor. If you know the magnitude of A and you know the magnitude of B, and then you know the angle between them or can figure out the angle between them, then if you just take the cosine of that, you're of course picking out the parallel component. And so the magnitude and angle method of the dot product is probably the one you'll find the most useful in this class, right? So magnitude of A times magnitude of B times the cosine of theta. And as theta, of course, goes through 0 to 360 degrees, it is sometimes 1, and it's sometimes negative, and it's sometimes 0. And those all have good physical interpretations, which we'll talk about in a second. So, for instance, even without any numbers, we can figure out if the work done here is positive, negative, or 0. So you might want to pause here for a second and think about your own answer. Right, so when I look at this, I say, formally, I can see that the theta here is less than 90 degrees, and the cosine of anything between 0 and 90 degrees is going to be a positive number, and so therefore the answer is going to be positive. Because if you think about this formula, magnitudes are always positive, and so any kind of plus or minus or 0 comes from the cosine function in this formula. The other way to think about it a little bit less mathematically, and going back to our original idea about work, is this force is in the direction of displacement, and it is responsible for displacing it, and therefore I am doing positive work. If this is me pulling a crate, for example, I am, doing work to the crate, and so positive kind of makes sense. All right, what about in this case? This is a 90-degree angle here. You might want to pause and think about your own answer. All right, so if this is a 90 degrees, then formally when you take the cosine 90 degrees, you get a 0 back, right? And that means that you're going to have no work done, letters C. Now, more sort of the physicality of this is what I was talking about with the perpendicular components, right? If you're pulling upwards on something, then you are in no way can take credit for any sort of horizontal displacement. And so you are not actually doing any work to the object with this force. Either it was already moving in that direction, or there's some other force that's doing work on it maybe to cause it to displace that way, but it's not due to this force. And so the work done by this force is 0. Okay, what about this picture? I'll pause here for a second, think about your answer. I'm just recording a lecture here. That was a longer pause than I intended. Had to put in a break there. What you can see here is that the angle between the two vectors is larger than 90 degrees. And therefore, if you take the cosine of anything that's between 90 and 270, then you get a negative answer for the cosine. So that's a formal way of looking at why the answer is B. But informally, you can say you are actually pulling this crate in the wrong direction for its displacement, right? So you're actively working against its displacement, right? You're trying to get it to displace less, not more. And that's the reason why a negative amount of work would make sense. All right, so here's one with numbers. So you might want to just pause here and do a quick calculation. Okay, let me walk you through this. So magnitude 4 newtons times the magnitude of 5 newtons, that gives me 20 newton meters, which is 20 joules. And then I've got to hit that with the cosine of 60, which is 1/2. So the answer is 10 joules, letter E. Okay, now I'm asking for the net work, which means I'm going to calculate the work done by each force and then add them up. And of course, it's scalars, so I can just add them up easily, unlike a net force where you have to worry about, finding all 3 components or whatever. So you might want to pause here, come up with an answer. All right, let me walk you through this. So this 4 Newton forces, this is the exact same picture as before. So we've already figured out that this one is doing 10 joules of work, right? 4 times 5 times cosine of 60. So we've got 10 joules of work being done by this force. Now this force is going to be doing negative work, right? Because it's a 120 degree angle, which gives you a negative 1/2 when you take the cosine of 120 degrees. And so you've got 6 times 5, which is 30. Hit that with the negative 1/2, so that's negative 15. So I have a plus 10 and a negative 15. So that sums up to negative 5, letter B. Right? So overall, even though this force is helping in the displacement to the right, this one is hurting more, right? Is working more against it than that one is. And therefore, the overall amount of work done by these two forces, the net work, is a negative number. Right? So I wouldn't basically use that first method, the component method with the x's and the sub y's and the sub z's, unless you're given vectors in component notation, right? And then it might be actually faster than going through and finding the angle. The other thing is that you should be careful about the angle, right? It's not the angle that either of the vectors make with the x-axis. The angle has nothing to do with the x-axis. In fact, unfortunately, I just gave you examples where the displacements were all on the x-axis, but the rule is it's the angle between the displacement, whatever direction that is, and the forces, right? And the force. And we went over this. Positive means they're working together, negative means the vectors are working apart, and 0 means the vectors are perpendicular. So, if you have angles of 0, 180, or 90, you don't really, of course, need to use the trig function. You can just say, oh, that's entirely positive, entirely negative, or 0. So here's some interesting things that come about from this definition that might not be intuitive, right, because of the way we use the word work in everyday speak. But if you're carrying something, right, and you are only applying a vertical force, in other words, you're just compensating for the weight of the object to keep it from falling, then as you walk back and forth horizontally, you're not actually doing any work. This man is not doing any work to the bag of groceries. As he walks to the right, and the bags are displacing to the right, as long as this pushes directly upwards, that is not responsible for any of that displacement. Of course, the dot product will give you, the cosine of 90 degrees and give you a 0 there. Now, at some point, he had to take that first step, and maybe he pushed it a little bit to the right with his chest, or maybe his hands applied a slightly angled force. So in the past, maybe he did some positive work to get the bag moving. But of course, as we know from Newton's first law, once you're in motion, you don't require any more force or work to continue in motion. Here's another one. Is any centripetal force, by definition, is not going to be doing any work, right? Because a centripetal force is directed inward along the radial line, And the motion, the mini displacements, if you like, the microscopic displacements are all in the velocity direction from 1 second to the next. Those are all tangential, right? And when that makes a 90-degree angle by definition. And so if you have circular motion, then your centripetal forces are never doing any work either. So it can be confusing, and I will try to be careful when I ask you a question, but there may be cases where you need to ask for clarification. If someone says, what's the work done in a situation, that's a little ambiguous, right? Because you should really be specific and request the work done by a specific force or the net work done to an object, which would mean you'd think about every single force that object is experiencing, find the work done by each one, and then add them all up, right? So it is common, and the textbook does it in a few places, and I may fall victim to it too, because it's clear in your own mind which work you're asking about. But work is, generally speaking, the work done by a specific force on a specific object, or it is the total work done to one object by all the forces being experienced on it. So the language needs to be precise in order for you to know what the question is asking. Now, why do we define work this way, right? And we define work this way because we're really concerned about energy, right? This is where we're headed, right? And this is something called, the formal idea is the work energy theorem, but it basically means we've defined work in this way, having these positive, negative, and zero values, because we're thinking about the energy that is being transferred to the object that we're pushing or pulling on, right? And so when you get positive work, that means you're giving the object energy, right? It's going to wind up, it's going to speed up basically. And when you do negative work to it, you're taking energy away from it. You're removing energy. And when you are applying a force that's at right angles and you're not doing any work, then you're not giving it any energy and you're not taking energy away, right? And so this connection between work and energy, and this of course is why they have the same units of joules, is that they are in essence the same thing, right? Work is the transfer of energy, the way we've defined it. Now, in everyday language, let's go back to my original thing where I'm pushing on the wall, right? If I'm pushing on the wall, then I am not doing any work to the wall, right? Because the wall is not gaining any of my energy. Now, I may be losing energy, but where is it going? Well, my muscles are heating up, I'm doing internal work with internal forces, displacing my muscles or maybe my arms are moving a little bit, right? And I'm generating heat, right? So I may be losing energy, right? But I'm not doing work to the wall because the wall is not the beneficiary of any of that energy. Okay, so here's a problem. You may want to pause here and think about your answer. Okay, so your first instinct is to say, oh, this is going to take me a little while. I've got 1, 2, 3, 4 forces, right, causing somehow overall this displacement. And so I can find the work done by this force, the work done by this force, the work done by that force, and the work done by that force. A couple of them are zeros, and then add them all up, and that will give me the right answer. But if you read the question carefully and think about the work energy theorem, the answer is embedded in there, right? What is the net work done to the 15-kilogram sled while it gains 28 joules of energy? Well, the gaining 28 joules of energy, that's the delta E on the right-hand side. How did it gain 28 joules of energy? It gained it by the work done on it, right? And so the answer actually has to be 28 joules of energy. And I think I made it work out so that if you take all these numbers, it does work out to give you 28 joules of energy. I'm not 100% sure about that. I haven't tried doing it out. But then the spirit of it was, this is an alternate way to find the work done, right? The total work done to an object, since it's also equal to the energy it gains or loses, you don't always have to go through the dot product of the individual forces and individual displacements. Okay, now how do you handle a non-constant force? Well, you shouldn't be surprised at this point in the course. This is kind of an old hat trick, which is if you don't have a horizontal line here, meaning a constant force, then what you do is you graph your force versus displacement, specifically the parallel component of the force, parallel to the displacement, that is, and you find the area under the curve, right? Because each one of these boxes is an F parallel times D, and so you sum it all up, and the area under this curve will give you units of joules and will be the work done by that force over that displacement. Okay, the other thing I want to define is power. Power is completely related to work. It's basically the rate at which you're doing the work, right? So you can find the work any way you want, either through F dot D or finding the change in the energy. And then you make something a rate, of course, by dividing it by the amount of time that it takes, right? So power is the rate at which you're doing work or the rate at which you're transferring energy. These are two ways of saying the same thing. So that is a joule per second, and that gets its own unit named after watt. So these guys, Joule and Watt, they're both scientists in the, I want to say, 1800s, I'm pretty sure. And they did a lot of early work with energy. And I think Joule is a French guy and Watt is a British guy. All right, so here's a power question. I might want to pause it here and think about what you think the answer is. Okay, if you want to raise a 5 kilogram mass, you got to think about what force would be required, right? Because the first thing before I find the power is I need to find the work done. And the work is the force times the displacement. The work, the force is going to be the force due to gravity, right? That's the minimum you need to lift something up with in order to raise it, is you have to counteract gravity. When you first start to lift it, of course, you need to be pulling a little bit harder than gravity, but only for that very first millisecond in order to get it started. Then, of course, Newton's first law takes over, and all you have to do is support the weight of the object as it travels upwardly on its own. So, long way of saying the answer is mg, so that's 5 times, let's round g off to 10, so that's 50 newtons of force in order to lift something. I'm going to lift it at a displacement of 5 meters. Since the force is up and the displacement is up, I don't need to worry about the cosine function. Formally, it's the cosine of 0. So that's 5 times 50 is 250 joules. Divide that by 5 seconds to get my rate, and that's 50 joules per second. So the answer is letter C. All right, here's another power question. You may want to pause here and see what you think your answer is. Okay, so we have a 45 watt light bulb, right? If you've ever bought light bulbs, you know that is the primary way in which they're described is by their wattage. And that is, of course, telling you the rate at which they're going to use energy. And that is, of course, related to how bright they are, right? Brighter bulbs need more energy because the light, of course, is a form of energy. So 45 joules per second for 1 hour, that's just rate times time. So I need to figure out how many seconds there are in an hour. That would be 60 minutes times 60 seconds. So that's 3,600. Seconds times 45 gives me 162,000, letter C. Okay, that's it for work and power. Thanks for listening.